In this video, we're going to be talking about properties of quadrilaterals, and then we'll get into a specific type of quadrilateral called a trapezoid, and we'll talk about the properties of a trapezoid. So to start off with just a quadrilateral is any four-sided figure or four-sided shape. This diagram right here is a generic sort of quadrilateral. Notice that none of the sides seem to be equal. None of the angles seem to be equal measures, and none of the sides seem to be parallel or perpendicular. So nothing special about this quadrilateral other than it has four sides. So we're going to use this basic figure to talk about the parts of a quadrilateral. And then we'll be able to apply these parts to more special types of quadrilaterals in future videos. All right, first of all, each quadrilateral has vertices, which are just points at the corners. So we have 4 points here, P, Q, R, and S. Name points using capital letters. Opposite in this context means across from, so angles that are across from each other, for example, would be angle P and angle R. That's not the only pair though. We have another pair here. We have angle Q and angle S are opposite angles from each other. So opposite angles are across from each other. And we can also have opposite sides, which again are just sides that are across from each other. So for example, side PS is opposite from side QR. And on the other side, side PQ is opposite from side SR. Next, we got consecutive parts. Consecutive means next to in order. So if you were to walk around this shape, what side would come next? It really depends on what side you start with. So this is not going to be the only order we could do, but just for an example, if we start with side PQ and we go counterclockwise, well then the next consecutive side would be QR. So PQ and QR are next to each other, they're consecutive sides. If we went the other way, it is also true that side PS and side QP are consecutive. So it just depends on what direction you decide to go in. So if we name these pairs of consecutive sides, we could go PQ, then QR, we could then go SR, and then PS to finish it off. Not the only way we could do it though. We could also have angles that are consecutive. In the past, we called them same side angles because they were angles sharing a side. So for example, P and Q are angles that share this side, so they're called consecutive or same side angles. So P and Q are same side, P and S are consecutive or same side, angles S and R are consecutive or same side, and lastly, angles Q and R are consecutive or also called same side angles. Lastly, each quadrilateral has what are called diagonals. Diagonals run diagonally usually, but more specifically, they are segments that connect opposite vertices or opposite angles here. So if we draw a line from Q to S, that's a diagonal. And we could also have a second one if we draw a segment from P to R. That segment is also a diagonal. So in future lessons, we're going to be talking about these parts, and they're going to be included in properties of other shapes. So be able to identify what we say when we say opposite angles are congruent, or consecutive angles are supplementary, or diagonals bisect each other. Those are just some of the examples of properties we'll have in the future. So study those terms, be able to identify those parts. What's also true about quadrilaterals, any four-sided shape, is that the sum of the interior angles is always 360 degrees. There is a formula for finding the sum of interior angles of any polygon, and what you can do is take the number of sides and subtract 2, and then multiply that by 180. This number of sides minus 2 is actually going to tell you how many triangles you're able to use to create the polygon. So in a quadrilateral, if we have 4 sides and we subtract 2, that tells us that we can create a quadrilateral using 2 triangles. Each triangle adds up to 180 degrees, so 2 triangles would be 2 times 180, which is 360 degrees. So using that knowledge, we can solve for unknown measures in quadrilaterals as long as we're given at least 3 angle measures out of the 4, or if we're given some algebraic expressions to represent some angle measures. So like in this first example, we could set up an equation to solve for x because we know that all four angles are going to add up and equal 360. We could combine like terms and solve for x. And we find out that we have 105 degrees missing in that quadrilateral. Part B is a little trickier, but the same process. We're going to add up all four angle measures, knowing that it's going to add up and equal 360. Again, combining like terms, 89, 51, 4, and negative 8 is going to give us 136. 5x and 3x is going to give us 8x. 2 steps to go. Subtract 136 from both sides and divide both sides by 8, and our x value is 28. All right, on to specific types of quadrilaterals. We're going to start with trapezoids, and then in a future lesson we'll talk about parallelograms, rectangles, squares, and rhombi. So a trapezoid, its most basic definition is that it has exactly one pair of parallel sides. So different from this quadrilateral that had no parallel sides. If we have a quadrilateral with one pair of parallel sides, we can call it a trapezoid. There are 3 basic types of trapezoids. Just a generic one with just one pair of parallel sides. We could have a right trapezoid, which is a trapezoid with one pair of parallel sides, and probably at least 2 right angles, although 1 is enough to call it the right trapezoid. But if we have one right angle here, it's probably going to be perpendicular with the parallel side across from it. And then thirdly, we have what are called isosceles trapezoids. Maybe you noticed that trapezoids are really just triangles with the top cut off. And so a lot of the properties of triangles are going to translate to trapezoids, especially the isosceles trapezoid, which is just an isosceles triangle with its top cut off. All right, here are the parts of a trapezoid. Parallel sides, which we can recognize by those arrows, are called bases, similar to a base in an isosceles trapezoid. The non-parallel sides are called legs, again similar to our triangle vocabulary. So we recognize our bases like A, B, and DC in each of these examples as being the parallel sides because of those arrows. That means that the other 2 sides are non-parallel sides, and we're going to call them legs. So AD and BC in each of these examples are the legs. Angles that are attached to each base, for example, angles A and B, are called base angles. Also down at the bottom on the other base, we have angles D and C. Those are also a pair of base angles. In an isosceles trapezoid, we have a specific relationship between those base angles. Just like in an isosceles triangle, base angles are going to be congruent, but because the top got cut off that triangle, we also have another pair of base angles, so they're also congruent. So 2 pairs of congruent base angles in each isosceles trapezoid. And one last thing about isosceles trapezoids, it's also true that if you draw diagonals, for example, segment BD and segment AC, they end up being the exact same length. So we say that diagonals are congruent. Besides just angles, we have another special piece of a trapezoid. It's called the median. And you can find the median in this first example of our trapezoid. This segment EF, notice that it's connecting the midpoints of each of the legs. And that is right in the middle of our trapezoid. So median means the middle. So the median of a trapezoid is the middle of a trapezoid. We can actually find the length of that by just taking the average of our 2 bases, or for example, finding the middle of our 2 bases. So if we add the lengths of each of our bases and divide by 2, we're finding an average of 2 numbers that way. You can also think of it a little bit differently. You can think of it as half the sum of the bases. So if you add the 2 bases and cut it in half, or multiply by 1/2. That's the exact same thing. So use either form here of this equation and interpret it either way it makes sense to you. Let's practice finding some angle measures and some median lengths. In this first example, given the isosceles trapezoid, let's solve for the unknown angles A, C, and D. Given the measure of angle B is 115 degrees, well, if it's an isosceles trapezoid, angles B and C are one pair of base angles. They should be the exact same measure. So angle C is 115 degrees. The next step is a little tricky. Knowing that consecutive angles are supplementary, we could find the measurement of 65 by subtracting 115 from 180. Two angles that add up to 180 are supplementary. So subtract what we know from 180 to figure out what's missing. Another way that you could do this is you could add up what we know. We know 115 and 115. Combine those and we get 230. We know that we have to add up to a total of 360. So if you subtract 230 from 360, you get 130 degrees left over. And since we know that these two angles are equal, we could divide that remaining 130 degrees in half and get 65 degrees for both of them. All right, let's solve for a median length. Knowing that this top length is one base and the bottom length is another base, and that this length in the middle is the median, we can add up our two lengths here, our two bases, and divide by 2. Or we can take half of the sum of 6 and 12. So 6 and 12 add up to 18, and half of that is 9. So our median length must be 9, an average of our two base lengths. One last time, a little bit trickier here. Test your algebra skills on this one. Knowing that 7x minus 2 is one of our bases, and x plus 12 is the other base, and 5x represents our median length, we can set up our formula to say that 7x minus 2 plus x plus 12, combining both of your bases, cutting that in half should equal the median, which is 5x. One way that we could solve this is we could undo our division of 2 by multiplying both sides by 2. It's always nice to get rid of a fraction. You could have also combined like terms on top first and then multiplied both sides by 2. That's fine. I chose to multiply both sides by 2 and then combine like terms on top. So 7x and x is 8x. Negative 2 and 12 combine to give me 10. Let's get our variables on the same side. We don't like our variables to be on different sides of the equation. So we're still combining like terms. I'm going to move the 8x over across the equal sign by subtracting or doing the opposite. 10x minus 8x is 2x. So one last step, divide by 2 to solve for x, and x is 5. All right, one last thing that we're going to do is we're going to prove a type of quadrilateral. In this video, all we've talked about are trapezoids, so we're going to attempt to prove that given 4 coordinates here, we have a certain type of trapezoid. So the first thing we want to do is plot the coordinates that we're given, and then take a look at what the shape looks like after you connect all your points. That'll give you a clue as to what you need to prove. So if it looks like a trapezoid, well then let's think about the properties of a trapezoid. There's really only one. We need one pair of parallel sides. So to prove that this is a trapezoid, we need to prove that we have a pair of parallel sides. So we might want to look at what appears to be parallel. It seems like side AP and RK are parallel. So if we just check their slopes, we should be able to see that if they have equal slopes, we know they are parallel. So finding the slope of PA, using our slope formula between those 2 points, we're going to subtract our y values or find the rise, which is 4, and subtract our x values or find the run, which is 2. And 4 divided by 2 could reduce to 2, or we could say that that's 2 over 1 if we want to keep it as a ratio. Slope of KR, done in the same sort of process, just using points K and R instead. Find the rise between -1 and 7. That's a difference of 8. Find the run between 1 and 5. That's a difference of 4. So 8 divided by 4 is still 2, or 2 over 1. Or using the slope formula, sometimes you get a negative over a negative, which we can simplify to a positive. So we end up getting the exact same slope here between those 2 points, 2 pairs of points. So we know for certain that those 2 lines are parallel. We can mark it. But it also appears that this is more of a specific type of trapezoid. It's not just any trapezoid. It might be a right trapezoid. If we think that these 2 angles might be right angles, we can also check the slope of PK here. And if it ends up being an opposite reciprocal slope from these other parallel lines, then we know that those 2 lines are perpendicular instead. So one more time, finding the slope of a segment or a line. Find the slope between the 2 points P and K. The rise between P and K would be the difference in the y values, that's 3. And the run would be the difference in the x values here, so that's a difference of 6. And then we know it's a decreasing line, so we know we have a negative slope. Or you can use your slope formula to prove all that. So -3 over 6 reduces to -1 over 2. We can now compare that to 2, or 2 over 1, and see that they are reciprocals and they're opposites. One is positive and one is negative, and they are fractions flipped from one another. So that tells us that we do in fact have perpendicular lines and a perpendicular intersection making 90-degree angles here and here. So now we can definitely say that this is more than just a trapezoid, it's a right trapezoid. We could say all of this math and some symbol conclusions here. Segment PA is parallel to segment KR, and segment PA is perpendicular to segment PK, and segment PK is perpendicular to segment KR. We got all that from this slope math, but we also want to just say it in words. Try and explain it as clearly as possible. So quadrilateral park is a right trapezoid because it only has 1 pair of parallel sides, and one of its legs is perpendicular to its base. Lots of different ways that we could say that. That's just one way that we can do it. So in the future, we're going to be continuing to prove types of quadrilaterals given 4 coordinates. And we're going to check our slopes of our sides. Eventually, we're also going to check the side lengths. And then eventually, we're going to find the midpoints of our diagonals to see if they bisect each other. But we'll do that in a future video. Good luck practicing trapezoids and just generic quadrilaterals.